Hi, welcome to the Fundamental Theorem of Calculus. This is where we will end this this little part of our break before part of our unit before spring break, and we're going to take about 15 minutes today to work on the Fundamental Theorem of Calculus. So it seems really foreboding, and what we've been doing in class has been a little confusing with how I changed things up with Desmos. I wanted to give you all a little bit more ground to stand on here with this lesson. So to do that, we need to talk about this fundamental theorem of calculus that allows us to find the exact area under any curve. And I should have also made this word any important. So any curve here for us is going to mean polynomials, rational functions, things that are continuous. They don't have any breaks, holes. We're not going to be looking at piecewise functions, at least not on this side of spring break. So we are going to be just looking at curves like polynomials and rational functions and radical functions. So typical stuff like what we did with derivatives. So we're not going to see problems where we cannot use this fundamental theorem of calculus. Now we actually already know how to do this practically, but I wanted to provide some more meaning behind it for you. And to do that, I have like what the theorem says, and then we're going to talk about it visually. So the theorem says that if we have a continuous function on the interval a to b, so here's a and b, then this capital F, you can see the difference, it's very, very slim. This capital F is any function that satisfies the equation. The derivative of capital F is the original function f of x. Or in other words, capital F of x is the integral. So that if we took the integral, I'm spelling it wrong. If we took the integral of capital F of x, which is what this says, then we should end back up with the original function f of x. So it's just kind of giving us parameters on what the notation is saying. And if those things are true, then we can find a definite integral with this operation. So we know this integral sign from a to b, so summing the y values multiplied by the change in x values, that's the definite integral. Is equal to the indefinite integral. So I should say capital F of x is the indefinite. Capital F of b, that's the indefinite integral of b. Minus the indefinite integral of a. So if we were asked to calculate this by hand, then we could do that. Fortunately, we can perform these operations. If you look down here at our next set of missing text, we can perform the operation in our calculator, or the way I'm showing is with Desmos. There's other solvers out there, but Desmos is going to be the most reliable one for us. So how we're going to use this is we're going to evaluate definite integrals with Desmos, which you've already done. We are going to do it by hand just so you can see. And if I'm going to ask you to use this on a test, then of course you can evaluate an integral with Desmos, but if I'm asking you to evaluate it by hand, I might ask you to like check somebody's work. So it is important to see how to do that and to actually use the fundamental theorem of calculus. Determining the area between two curves is the third thing that we'll be doing with this activity, or with this theorem. So before we move on, the fundamental theorem just has this subtraction of two integrals here. We know that this is an integral means the area under the curve. So what this is actually saying is take the, I'm going to say area under the curve, AUC, from 0 to b, and then subtract it from the area under the curve from 0 to a. So the integral, I guess, area that we're finding here is going to be, if we look at the graph, it's almost like we have this red region. Well, let's use blue. We have this red, or this blue region that is B, the area from 0 to B. If I can quickly kind of highlight this in. And then we have, we can find that with the integrals, with the definite or indefinite integrals. And then we can subtract off the area under the curve from 0 to a. So we would just subtract off this bit underneath the curve. And this works for any curve. If you remember before, we were looking at, I'm in the wrong one. Before we were looking at the area under the curve with just simple geometric shapes. Now we have more complex equations we can use. And this is going to be a lot more flexible for us if we can use this to then evaluate the area under the curve for things like polynomials or something like that. And we might see it manifest in different ways after spring break when we look more at integral applications. But for right now, we're still getting the feel of like what are we actually calculating for these integrals. So we're going to first, with number 1 here, we're going to first set up the definite integral and evaluate it using Desmos to determine the area under the curve for this function, y equals x squared minus 8x plus 17. And we're going to evaluate it from 1 to 4. So luckily with these problems that I'm giving you for practice, there is a nice graph and you can see sort of what you're finding. Because I hope you all are attaching the integral operation to an area under the curve. It's super important that you are equating those two, just like you equated the derivative operation with the slope of the function. So we're going to put this into Desmos to solve. Right, so there's the setting up part of the directions. I've set up my definite integral with the function itself inside the integral operation and evaluating it from 1 to 4, from x equals 1 to x equals 4. So for my Desmos evaluation, that's exactly what I'm typing into the calculator, the graphing calculator, or you can go to the scientific calculator and it'll work for you. Being careful to use parentheses. So we get 12. So we get an answer that is 12, equals 12. All right. And now we are going to try and get this same result by using the fundamental theorem of calculus. So the FTC says that we are taking the integral of x squared minus 8x plus 17. And we're going to use the indefinite integral here. But we want to evaluate those indefinite integrals at 4 and 1 because those are our bounds, and that's what this fundamental theorem of calculus says. If I zoom in some, just to look at all this detail, the end bound is what we evaluate with first, and then the bottom bound is the start bound, and that's what we subtract at the end of this operation. So this is how I set it up by hand, and I'm going to find the indefinite integral. So 1/3 x cubed minus 4x squared. So this should be old news for you guys, just finding an indefinite integral. And then I need to evaluate this. And so there's this notation we use when we're evaluating this by hand, which is this bar at the very end. We don't use plus c anymore because we're actually using an indefinite integral to evaluate a definite integral. So we are actually keeping those bounds to show that we're going to plug in 4. We're going to substitute in 4 for x and subtract the equation of plugging in 1 for x after that. So I'm going to write 1/3 4 cubed minus 4 to the 4th squared plus 17. And then I'm going to subtract that from, so here's my subtraction between the two. It's the same like general formula for the answer to an indefinite integral, but we're going to subtract 1/3 times 1 because we're evaluating with 1 now, minus 4 times 1 squared plus 17. And what we got to be careful of is if we are going to evaluate this by hand, is we need to use parentheses because we are subtracting, and we want that subtraction to apply to everything. And so before we move on here, because I mean we already know the answer to this problem, I want to make sure that you know that I did use that 4 and that 1 to evaluate my indefinite integrals at a certain point. And so if I did this properly, then this equals what my Desmos answer was. And so I would have to plug all this back into a calculator, and I would get my 12, just like I would if I just let Desmos calculate it for me. So the fundamental theorem of calculus is sort of why our definite integral works when we use Desmos. And our friend Leibniz was able to figure this out for us. So thanks, Leibniz, famous mathematician there. Okay, so we've got just 1 more minute, and I'm going to look at this area under the curve, or sorry, bound by 2 functions. So this is where we get to use Desmos again. We're gonna write this definite integral, and then I don't believe we're gonna get to this extra example. We might get to it in class, but we're definitely gonna hit this one right now. So this is actually a unique, one of the really cool things about calculus, I think, because we can start figuring out some strange areas and representing areas that we normally couldn't. So we have this like blue highlighted region that we're trying to find the area of, and it's bound by all these equations. So we have a parabola, we have a line, and then we have at the very end we have 2 vertical lines. So I hope you can see those in the graph. It's important that we have these because we're going to use them to delineate the area given. So we're going to write a definite integral that means the area between those 2 curves. So we're actually going to take the integral of what's underneath just this diagonal line. So we got this diagonal lines area under the curve. And then we have the area underneath or between the x-axis and this parabola. There we go. So we have this crazy area between the x-axis and the parabola because it crosses that x-axis. So here it is without me having that orange area in there. So the orange area that I just was talking about is kind of easy to describe. So we're going to use our bounds. So from 0 to 4, and I'm sorry, I'm going over time a little bit. So from 0 to 4, I want to integrate my linear function, so x plus 2. And then I want to get rid of my my green area. But notice what's going to happen when I get rid of my green area over the same interval. So my green area is defined by x squared divided by 2 minus 2. Is when I subtract away the positive green area, let me get rid of this orange so we can see it better. Here's my positive green area. When I subtract my positive green area, that's definitely going to take away some of the larger orange area. But when I subtract a negative green area, which is down here below the x-axis, that's going to add some more area on. So subtraction is going to help us do that. As long as we can find which one of these equations is on top. And we know that the linear function is on top. So we write that first when we subtract area, when we subtract functions to find area between curves. So that's a mouthful for me. So this quadratic is what we subtract from the orange linear function when we're talking about integral operations. So Desmos can calculate this too, and using that we can get an answer. Alright, so there's the calculated area using Desmos. And you can see that I've used parentheses. I've bound things with my 0s and 4s, and I have subtracted the quadratic from the linear function in terms of which function goes first in that subtraction process. So all this is possible because of the fundamental theorem of calculus. Desmos has made it even easier because we can just tell it to calculate an integral. Yeah, that's going to be it for class, for the video. We're going to practice some more in class, so be on the lookout for a page to, well, we're going to practice before class as well. Be on the lookout for that homework that's paired with this video. And just practice using Desmos to calculate. And if you can, try the problems that are used to that are asking you to use the fundamental theorem to calculate a definite integral by hand. Thanks for watching. Bye.